All right, this is chapter 3, plate tectonics. This first section, we're going to be going over the evidence of plate tectonics. So, what are plate tectonics? Well, tectonics definition is the study of large scale movement and deformation of Earth's outer surfaces. Plate tectonics is just those pieces of what they call rigid plates moving over a weaker, more plastic layer in Earth's upper mantle. So, they're not really floating, but kind of gliding on slime more than like a log floats on water. But they're moving around. And so here are a couple of different plates, as we call them. These are some continents here. Um, and how did this theory come into being? It really started with Alfred, I think it's pronounced Wegener, published the idea of continental drift, in which he realized, as you can see here, that these continents kind of fit together. We have Africa and South America, and it looks like somebody just tore them apart. So he put that together, and he also realized that things on the continents, not just the shapes, but things on the continents lined up as well. So if you imagine um, fossils, glacial, geologic data, you had fossils that connected across. You had geologic data on some continents, mountain ranges were kind of torn apart. And so a mountain range would, stop and then continue on the other ones. Fossils, even tracks, really, you line them up and you can see tracks on one side and tracks on the other side that line up, same exact tracks from the same time and everything. So all of that kind of fit together that, hey, maybe these pieces on the globe were once put together. And then once we got some improved maps, we really were able to see that, yes, like they really do fit together. That's the way. All right. So, like I was saying, here are some of the fossil evidence. So, this is Pangaea. This is probably the most famous supercontinent because it was the most recent one, but there have been other supercontinents before then where everything just kind of like on a conveyor belt, but it's the globe. So it ends, it's a circle, and they kind of come together, they crash together, then they get pulled apart, and then they crash together somewhere else. But Pangea was the most recent one. And so looking at here are some of the fossils. So these different fossils were found right here, as well as right here. Um, you put them together and you can kind of see, like, oh, this animal ranged right here, which makes a lot more sense than the same animal being on different parts of the globe, where you're going to find completely different, now, if you look at South America and Africa, completely different climates, different vegetation. How would that one animal be in like a desert in Africa and be in a rainforest in South America? Let's just say I don't actually know if this is where the desert is in Africa, but theoretically speaking, and know that and have that animal exist in both of those different climates. Like this makes so much more sense. Same thing with the glaciers. Have evidence of glaciers here around Antarctica with the glacier spreading out over the continents. Again, putting it all together in this with Antarctica kind of being in the center makes a lot more sense than um, random glaciers all over the continent and what could be closer to the equator. It just wouldn't make any sense nowadays. Um, Glacial sedimentary rocks indicating again climates, plants, and things like coal. Coal forms from swamp, kind of warm environments. You're not really going to find coal, in cold areas. So a lot of these things started making sense once they realized, oh, that's because the continents are no longer in the same place that they are now, and they used to be placed on the globe where it would be colder or where it would be warmer, and that would match all this evidence that they were looking at. And not all the continents record warming or cooling trends at the same time. So that's just to say, if the whole planet, like that theory of what global snowball Earth, where like they say maybe the whole Earth was covered in ice at one point in time. Um, I mean, that's all the continents everywhere. Not maybe this one's warming up and this one's cooling down. And so, since they didn't see everything at the same time, you can't say it was like a global warming or cooling trend. It was definitely more of just like a localized, you're in a like at the poles it's cooler and at the equator it's warmer kind of trend, location trend. Evidence of drift. All right, so besides that, as we got more and more advanced technology, we were able to look at the ocean floor. We have mid-ocean ridges mapped here, where we have a lot of mountain ranges. We can't see them because they're underwater, but if you were to go and look at the topography of the ocean floor, very large mountain ranges all right here, and they are volcanic as well. We have trenches along some of our continental coasts. Um, the Aleutian Islands up here, and Japan, other side, so over here. This is all around the Pacific floor, the Pacific Ocean. We see the age of the seafloor basalt. So if this is age here, we have the youngest is red and it goes to oldest, gets into the blues and purples. And so by the mid-ocean ridges, we have the youngest material always. Um, and same thing with the sediments. The sediments are also youngest near the ridges. So it goes young to old as you get towards the continent everywhere you go. Not only does it go young to old, they were able to see these patterns in the magnetic material. And so, let's see. All right, so, anyways, I don't know how to start this. As the magma's coming up in that mid-ocean ridge, um, so you have volcanic material. It is molten, it's not solid. So the iron, little pieces of iron in there, they align to the magnetic north. And then they're pointing to north, and then eventually the lava cools into a rock, and they are stuck forever in that pointing north position because once it's solid, those little pieces of iron can't move anymore. And we have found out, I think the physicists and geologists, but that there have been reversals in the pole throughout the history of the Earth, where sometimes magnetic north actually points south, and sometimes the iron pieces point to what is today north, and it goes back and forth through time. And so, if a piece of magma or lava solidified at a time when the magnetic north was actually towards the North Pole, then those would have been stuck forever in place, pointing south. Um, and as they go through and they read the magnetic direction of the ocean floor, then they see that on both sides of the ridge, they see the exact same pattern. So it'll go from positive to or positive. So north, south, north, south. And the time frame, so the thickness of these bands on both sides of that spreading ridge are the same. So like you can see this one here was a relatively short time where it was facing south, and that equals this one, which is a short time facing south, which is a little bit shorter than this time here. And so they see that, and so they can start building this concept of, okay, well, it is like a conveyor belt, and we have two conveyor belts, one going this way and one going that way. And then we can kind of map um, well, the time based on the magnetic reversals. Let's see if I covered everything. Yes. And so with the magnetic reversals, actually, if I go back, you can see, and I think we all know this, that the North Pole kind of will like wiggle a little bit through time as well. And so it's not always even in the exact same spot. Like sometimes North could point here, sometimes North could point here. Sometimes if it was in a reversal period where it's pointing south, sometimes it can point here, here, here. But it's still kind of generally around the poles, but it's not exactly. like what we would plot out on the globe and say this is north. Um, so with that, they can go through and they can create these polar wander curves, which are actually quite complicated, but they can look at um, the ancient iron pieces in rocks. It doesn't have to be basalt or a lava rock. It can even be sedimentary rocks, because if you think of like grains floating through a lake, then those are going to float and they're going like a compass on the, in the water. They're going to point to the magnetic north as well, and then kind of solidify as they turn into rock, as they go from like pieces of clay into claystone or whatever. So they can do this on the continents as well. It doesn't have to be the ocean floor. And they can go through and say, okay, well, based on this rock, which is this age, and where they have figured the pole would have been pointing at that time, then they can figure out where on the planet that rock was. And if that rock is on a continent, they can kind of place a continent. And so they can build these historical paths of where the continents have moved through time. And so they put that all together and they can see here. And so here we have Laurasia and Gond Gondwana. I think this is right after Pangea is starting to kind of break up. So it's kind of like two major continents, and they've put in these little rifting zones for you so you can see that. And then it breaks apart a little bit more 100 million years ago, and then this is what it looks like today. And that is it for kind of the theory and the evidence for plate tectonics.